Hello, everyone. And now we will start this section. And in this section, we will have 3 talks. And the first presentation will from the Professor Wang from Texas. So let's welcome.
Thank you. Good afternoon. Yeah, I will give you a brief introduction about subsidence monitoring in Houston. So in Houston, we start to monitor subsidence very early. I think earliest leveling data started from 1906. So it's over 100 years. So we can divide the whole history as a leveling age. Yeah, that mostly before the middle of the 18th. And then I will recognize the later part as GPS inside age. We have the TISOmeter across the two from 17.5 to now, so it's already 55, 65 years old. So mostly my work focus on the TISOmeter and the GPS, but recently I also work on the inside and also target data. I find target data is amazing. So this map from USGS, it shows the accumulated subsidence from 15 to 2001. So in the ship channel area, it's over 3 to 4 meters. So this one shows the subsidence during the past two decades, in fact, 25 years, derived from GPS. So you can see this one is 10 centimeters. In Jersey Village, in this area, it's over approximate to 1 meter. But luckily, you can see this part, the previous rapid subsidence area, but now it's this part, subsidence southeast, subsidence stopped. Yeah, so it's a big change. Subsidence propagate to the inlet with the following the propagation of the population. So this is a summary of the subsidence history in Houston. So the blue one is the southeast. You can see most rapid subsidence occurred in 16, 17, 50s, and then slowly slowed down. But in the northwest, subsidence continues. Yeah, from several meters to now, still about 7 to 8 millimeters, 1 centimeter per year. It has been continued for 5, 6 decades. As a result, the compaction of the two places are different. For the old one, southeast, compaction continued much shorter, just 3 decades. But for the northwest, continued for 6. So in the southeast, subsidence, we already finished a subsidence cycle. It's finished. Rapid subsidence stopped. Yeah, so groundwater, so this is the groundwater, already reached the pre-consolidation head. I call the new pre-consolidation head. But in the northwest, no, still about 20 meters below the new pre-consolidation head. So we need to wait until this groundwater reached to the new pre-consolidation head. It will stop. So this is a cycle of consolidation. I will explain a little bit more. So we found in Houston, subsidence most concentrated in the top from mostly top 600 meters. Below top 600 meters, compaction associated with groundwater withdrawal is minor or ignorable. Yeah. So luckily they installed a TISOmeter. In Houston, we have 14 now. The new one installed about 5 years ago. So we didn't use the new one. This one is in KT, but we do use others. So a TISOmeter is designed to measure the compaction. It's only measures the compaction between the lead surface to the bottom. If there's something below, no, it will not count it. So this one shows the geodetic infrastructure. So we have density GPS network. So as last year, we have about 250. But in fact, it's over 300. We don't count something that has a history less than 3 years. Yeah, it still increased with about 10 stations per year. And the subsidence district try to switch some previous campaign to the continuous. So we will have more and more valuable data. So this map shows the change of subsidence during the past 2 decades. So the subsidence contour. The blue one, hope you can see, that's the 1 decade before, from 2001 to 2009. The red one from 2011 to 2020. Clearly you can see the subsidence area is shrinking, and overall subsidence rate is reducing. That's a very good result. We exactly told what we expected. So I will focus on the major results. I think the first major result is pumping is the primary reason causing urban subsidence. You say, okay, of course, everybody knows this now. But think about 100 years ago, 65 years ago. Yeah, people really don't know that. Based on the very limited observation from leveling survey and groundwater measurements, the subsidence community in Houston, they figured out, okay, groundwater could be the primary one. So they set up the subsidence district. And quickly, the subsidence district make the regulations focus on the subsidence, focus on groundwater withdrawal. Just try to reduce the pumping. It works very quickly. I would say very quickly, the Southeast subsidence reduced. So based on the field observations, subsidence district, they repeatedly or regularly update the regulation plan. That's great. So the new one is amazing. They really give some flexible for the people to use the water, but finally you reduce the use of the water. So this map shows the current subsidence rate, most of the last 5 years. Major funding tool, new pre-consolidation head. Luckily, in Houston, we have a very consistent long-term observation. So this one observation from Pasadena ectensometer. Yeah, if you look at this one, this INSA compared with the GPS contour. Of course, they agree very well. Past 5 years. So people will ask, I think everybody will ask, when will subsidence stop in the Northwest? Yeah, because you show the trend, it's reducing, it stop. Another question is how to prevent subsidence to reoccur in the Southeast. Yeah, we know subsidence can reoccur if you pumping again. So in fact, I found these 2 questions are the same question. You can use one term or one criteria. That's the pre-consolidation head. So in the Houston area, we already finished in the Southeast area. We already finished a cycle of consolidation. So subsidence started from the 40s. So the groundwater level at that time, yeah, close to the pre-consolidation head. I call this as historic pre-consolidation head. Once groundwater level breaks through that level, rapid subsidence, inelastic subsidence will start. Continued, and then reach the max drawdown. Because of groundwater regulation, groundwater level start to the elevation. Somehow, you will see a net rebound. Yeah, you observe from GPS or from the ectensometer. So net rebound is a very good signal to show you that, okay, now the compaction in clay stopped as the inelastic in sand started because your groundwater level is increased. Yeah, increase. That's the loading effect stress is reducing. So that's an inelastic rebound from sand. So we found that this time is the new pre-consolidation head. I think I should call post-consolidation head. So it's a consolidation at the consolidation cycle finished. So maybe next time I call post-pre-consolidation head. You can see a very beautiful net rebound in this area. 2 millimeters per year, already continued 3 decades. I think sooner or later that rebound will stop. Yeah, elastic, it will stop. And then you may see the slide subsidence. I think that will be the lateral subsidence. Okay, so this is a consolidation process. So I figure out that maybe it's a good summary to call as 4 phases: prior to pumping, early pumping, excessive pumping, and regulated pumping. So prior to pumping, that's over-consolidated. It's over-consolidated. Groundwater level was higher than the historic pre-consolidation had. They could have some inelastic one, but they will not have the rapid inelastic one. But now, the groundwater level in southeast of Houston is above the new pre-consolidation height. Subsidence stopped, even saw the rebound, so it's over-consolidated again. Okay. This map shows the groundwater level in the 20s, 30s in the Houston area. UAC skipped it. Yeah, you can see at that time, most groundwater level in the Chico at the imaginary aquifer is about 10 meters around, 10 meters. As I mentioned, this groundwater level is not the historic pre-consolidation height. It's over-consolidated. During this period, subsidence is still elastic until at the end of the 30s or beginning of the 40s, that groundwater level was the historic pre-consolidation height. So it's about 10 to 20 meters lower than this one. In Houston area, we have 10 ectasometer sites. Yeah, 10. So we have the very consistent ectasometer work as a two. One is compaction, one is groundwater well. Yeah, so we have the consistent measurement of groundwater level change at the land subsidence. So for 10 of them, I found those three numbers for each of them. This is a historic one, pre-consolidation height. This is max drawdown, and this is new pre-consolidation height, so that you observe that rebound. So you only use the 10 samples. So yeah, 10 samples is already a lot for us. You use 10 samples, I figure out a mathematical formula like this. So how to project the new pre-consolidation height. So we have the historical one. We have the max drawdown. And then, so this is the historical one, max drawdown. So this change from this point to this point. We know that the new one should be below the historical one, should be above the max drawdown. So amazingly, I figure out this number that you can apply to all of these 10. So here, K is an empirical coefficient. It's suggesting the potential maximum time span that would allow the hydraulic head in the aqueduct class to lower to the MDD, max drawdown. So it takes possibly 1 century. But anyway, so this number, I figure out that works for all. So T is time from this point to this point. So this T is the time that once you groundwater level reach the max drawdown, subsidence still will continue. In Houston area, mostly they continued for 1 decade. For this site, 1.5 decades. So the rate of this subsidence, so this one, it's much smaller than the previous one. So I found T equal 5, I fixed at 5, that works for all of them. So use this mathematical formula, I can project or predict the new pre-consolidation height in other sites. Luckily in Houston, USGS archive 5,000 groundwater records. That means 5,000 groundwater wells. But most records only have 1 measurement or 2 measurements. So I wrote a script to find those kind of groundwater measurements. I call it V-shape. Yeah, so you clearly record a max drawdown. Mostly you don't have the historic pre-consolidation height. Mostly you haven't reached the new pre-consolidation height, but I can project the new pre-consolidation height. For historic pre-consolidation height, it will more like unified because it was generated or formed during a historic time. So for the regional, maybe so from my previous map, I just use different ones for different contexts like. So I use this formula to project the new, because this new pre-consolidation height will answer the 2 questions. When will subsidence stop? How to prevent subsidence to reoccur? Okay, this is my result. So I found in this part, this is the Davis County. The new pre-consolidation height is about 30 meters below the land surface. At the current groundwater level is about 13.5 to 13. So the new pre-consolidation is just 5 or similar as the current groundwater level. But in this area, the large part of HGST area, regulatory area 2 at this part. So new pre-consolidation height is 60 meters below land surface. Current groundwater mostly about 40 meters. So that means you have 20 meters higher than your new pre-consolidation height. So this is like bank or groundwater reservoir. Remember, we need to use groundwater, for example, during the prolonged drought. We need to allow people to use pumping somehow, or groundwater surface water was polluted. It happened in some other cities. A large area of surface water was polluted. We need people to pumping. But in this case, we can answer, okay, you can pump, but be careful. Don't control your pumping rate. Don't below this point. If you below this point, that will be the inelastic compaction, not recoverable. If you above this one, that's elastic, mostly elastic will be recoverable. So I think that's the application for the new concept of new pre-consolidation or post pre-consolidation height. Major finding 3. Yeah, we talk a lot about fault. Yeah, so our recent studies index that the recent subsidence. Okay, for example, recent 10 years. So in Houston, the recent 10 years, at least recent 10 years, we still have a widespread infrastructure damage, mostly parking lots, roads. Yeah, those pavements are particularly susceptible to damage from repeated seasonal subsidence. Yeah, repeated. One time doesn't do damage. But year by year, that will do damage for the parking lot or the overall pavement. So we did a study about the horizontal movement. We found that in Houston area, they do have widespread pavement damage, but the fault, GPS really didn't show any consistent or coherent horizontal movement along the fault. They show something about 1 to 2 millimeters per year along the non-point fault, but that was mostly caused by the subsidence bore. Yeah, in Jersey Village, in this area, they have rapid subsidence. So this 1 to 2 millimeter associated with subsidence bore. It's not like fault movement because along the two sides of the fault, our GPS, we installed a permanent GPS array with 10 GPS stations at two sites. They didn't show anything different between the faults. Our INSA results also didn't show anything different horizontal vertical movement along the fault. So we have interest in why there are still very significant infrastructure damage in Houston area, particularly in the long point, in the Jersey Village area, the current subsidence area. So we started the seasonal cycle. Seasonal cycle is elastic, okay, it's recoverable. So we found that so there is a significant seasonal subsidence in seasonal movement in the subsidence area. So this one, you can see it's up to 2 to 2, some area up to 4 centimeters in the subsidence area, this Jersey Village area, Kate area. But in the area subsidence stopped, amplitude of seasonal signal was very weak, below 1 centimeter sometimes. So we further do the more process, we found that, okay, it's really things like in your subsidence area, you have a large amplitude of seasonal movement. We further found, okay, so this amplitude is not caused by expansive soil. In engineering, they study a lot about expansive soil. First, mostly shallow about 2 meters. We found this is associated with the elastic compaction of a deep aquifer. This deep aquifer associated with the hydraulic head change in the imagined aquifer. You cannot stop this kind of seasonal movement with engineering methods. So it's from the deep. So engineering, they use a term called heave. They don't use uplift. So I just use the subsidence at heave. So the heave is uplift. So another result, that's natural subsidence. Yeah, in part of Houston area, Galveston. Also, projectic subsidence stopped. Subsidence still ongoing, in fact. So this is the 1 century extensor target, 1 century target. We excluded the other possible reasons. It consistently show 6.2 millimeter per year submergence. So submergence is a combine of land subsidence and sea level rise. In this area, with respect to our regional stable reference frame, GOM plating, stable Gulf of Mexico reference frame, sea level is 2.6 millimeter per year. So you after you remove the sea level, so land subsidence is 4 millimeter per year. Very steady, no change during the 1 century. Our GPS in this area, amazingly, it also shows 3 to 4 millimeter per year. Before we conducted this study, we say, okay, subsidence should be stopped, but it continues 3 to 4 millimeter per year. So this is natural subsidence. It's mostly rapid in Galveston area because of this part. So in geology, they use a term called Houston embayment. Only in the Galveston area, we have a very deep unconsolidated aquifer. So mostly from the Jasper aquifer. Okay, conclusion. I think the most important conclusion is that we need to continuously do the monitoring. So we benefit from the continuous and long history monitoring. Yeah, so other people at other groups show many observations from many sites. I always talk to them, try to keep them to alive for a century. That will give us some new results. Another lesson we learned is that use multiple techniques, as people show here. The community, we use leveling, we use extensometer, use GPS, use INSA. Okay, I will stop here. I appreciate your listening my talk.
Anyone have questions? Right.
Really interesting talk. I was curious. So that was I think a really useful equation that you showed that estimates your new preconsolidation head. And I was curious if you have tried, or maybe just thought about trying, comparing that with what you would get from different synthetic Ford model simulations, just to kind of test that against what you might see from whatever Ford model of consolidation theory.
Yeah, so everything is about reasonable because that's the only data we have. You really cannot find other data to justify or to something. That's the only data we have. So I think I do have prepared a slide here. Okay. So the one I prepared here, let me show you this one. So for this one, the ADEX. So the current subsidence is 7 millimeter per year. Previously, several centimeters. So 7 millimeter per year is still the subsidence. It's not lateral subsidence. So I calculate for this side using my equation. The new pre-consolidation head is 19 meters, 90 meters below land surface. So the current groundwater level is about 110. So that means you have 20 meters space to increase. That's close, in fact. That's close. I think that explains why the subsidence rate is small, millimeter, but didn't stop. So if we give increase 1 or 2 meters per year, then maybe in 1 decade, you reach the new pre-consolidation height. That subsidence will stop. Based on my experience, I think it's very reasonable according to the regulation plan in the Northwest. Yeah, in that area, if we continue like that, we give 1 decade, then the subsidence mostly stop. It's always talk about reasonable. Yeah, I think that is reasonable. And also for this map, Okay, I think. They can quick mark here. There. Okay, sorry. Okay, I think this is very reasonable. Look at example. In this area, you always show the V shape from the groundwater level, but subsidence still continues. It's still at the centimeter level. Well, when I checked, it seems it's still more than 20 meters below the new pre-consolidation height. In this area, it's same thing. Look at this area. Yeah, ground close to the boundary, subsidence just stopped. I found that I predict the new pre-consolidation. They agree very well with the current groundwater level. They are same.
Yeah, it looks like a really useful tool for, especially for management and many applications. Thank you.
What? Okay, it's actually more of a comment that I appreciate that you're exploiting recovery data, because there are very few examples in the world where we have water level recovery. And I think there's a lot of work to be done here. And if anybody can figure out how to put a pressure transducer into a clay unit without depressurizing it, that would be great. Next frontier.
Subsidence issues earlier, so we started earlier and we finished earlier.
Okay, thanks for. And next presenter also Professor Wang. Yeah. Hi.
Oh, I think my voice already allowed. Okay, so I will give you a brief introduction about the land subsidence in Tianjin. So you may know, this Tianjin is very close to Beijing. It's half hours away. Tianjin, Beijing have been suffering from subsidence for several decades. Yeah, they have the same problem like we had in Houston, or even worse. Yeah. Several years ago, to attend this meeting, we with colleagues in China, we prepared this paper. Yeah, so we processed paper at the end of 2019. Yeah, there are some GPS data. That's a good one. This one we call the Wuqing. This shows 5 centimeters per year subsidence. Wow, that's a lot. And this one here, adjacent to Tianjin, shows 3 to 4. It's even accelerated. You can see from 2 accelerate to 4. In the north part of Tianjin, it's the mountain area. Yeah, no pumping, and also the bedrock area, so no subsidence. So we prepared this paper. At that time, I was worried for subsidence. We like to do the projection as research. I thought, oh my God, you want to reduce 5 centimeters subsidence to stop several decades. Yeah, luckily I didn't include this projection in my paper, because I know we can make mistakes. Yeah, and also this is not a good news, so I didn't do that. So in fact, subsidence in Tianjin recorded by GPS is not the most rapid subsidence recorded by GPS I processed. Look at this one. We have friends show the Mexico City. Yeah, this one, MCC1, is subsidence recorded by GPS in International Airport of Mexico City. Well, this is real measurement, okay? 27 centimeters per year for 10 years. In fact, it accelerated since 2017. So almost 1 foot per year, the international airport. You may ask, okay, how often do they do the repavement? But this is real data. Even in Houston, in fact, the most rapid subsidence is about 2 centimeters per year. Yeah, the most rapid subsidence in Houston is only 2 centimeters per year now. Recently, I'm processing data in another part of China, Shandong. You can see GPS record beautiful 7 centimeters per year subsidence in Shandong, several centimeters. So this is the experience in Houston in the northwest. You can see 1 decade we reduce about 1 centimeter. 1 decade, almost on average 1 to 2, below 2, above 1. Yeah, so that's the reason I predicted that for Tianjin area, if you want to reduce a 5 centimeter subsidence to 0, you need 1 decade or 2 decades. So last year, I reprocessed data because for this meeting, we do the observation to use satellite data. We always need to redo it, because they always give us the surprise. So I reprocessed data. I found this one close to the coast area. Oh, that's nice, reasonable, from 2 centimeters per year reduced to the 8 millimeters per year. That's nice. So this one from 4 centimeters reduced to 2 centimeters per year. It's also nice. But this one, the most rapid one, Tianjin Wuqing, from 5 centimeters immediately they switch to the 4 millimeters per year uplift, like instantly. The problem is GPS data, they have a data gap here. I found surprise. You always have the data gap in the time slots that you think is the most important. Yeah, for many of my research I found, I lost data during the time I think I need the data. So I was worried, what happened during the gap? I think something is wrong because I believe this will not happen. You cannot switch subsidence from 5 centimeters per year to uplift just in several months. This like maybe several days, I don't know. So you can say this is Houston. Yeah, subsidence will reduce and then continue for 1.5 decades. Some place 2 decades to totally stop. And then you will see the lead rebound. At this site, you just immediately you see the rebound. So what happened? We have ideas for what's the reason, but I just didn't realize it can change so rapidly. So then this is a south to north water diversion project. Yeah, some you may know that. I'll just give you a brief introduction. So this is Yangtze River in South China. This is North River, Yellow River in North China. So this is Tianjin, Beijing. They designed the engineering project, try to bring the water from south to north. They designed with 3 routes, west, central, and east. The central one, the large one, start to bring the water to North China in the end of December 2014. So you can regard as the start of 2015. This one, the east one, start to bring water to Tianjin in 2021, in fact. It seems they transferred a lot of the water. So subsidence rate start to change after 4 years. Yeah, mostly occurred in 2019. It takes some time for the systems to switch from use groundwater to the surface water. It seems they switched in 2 years, and then for our aquifer have a delay to stop the subsidence or reduce subsidence. Anyway, start from 2019, overall you will have a subsidence rate change. So you can see here our INSA data, our process INSA data. INSA data will very well fill the gap. So now I believe this is a true change. Yeah, I believe this is true change. Of course, now I always can explain something. Okay, I say this is possible to happen. Think about it. If you immediately stop the pumping and your recharge is very rapid, and if your aquifer have a lot of sand, so the elastic rebound or expansion will offset your subsidence or your compaction. So that it seems at this site they finish this process to offset the compaction just in several months or 1 year. So this is the real one. So change from 5 centimeters per year to 4 millimeters per year uplift. Or in fact, I never saw 4 millimeters per year uplift in Houston. Most that we observed is about 2 millimeters per year. So that means in this area, they do have much more sand in the aquifer. Yes, if you read the literature, yes, in North China, yeah, the aquifer has much sand than Houston area. I'll give you some numbers, yeah, because those numbers are important. So this project was designed to bring 45 million cubic meters. I have no idea what's that number. So I compared with some number. So Yellow River, the annual natural flow is 58 billion. So that means this was designed at capacity of 2/3 of Yellow River. It's almost like another Yellow River. Yeah. So Yangtze River capacity is 915 billion cubic meters per year. So this like transfer 1/20th of the water, of the Yangtze water. Yeah, it's like take out 1/20th to the north. So during the past 7 years, from 2015 to 2021, so I stopped all of my data in the end of 2021. So totally they already brought 16 billion. So that's really like 1 year's total water volume of Yangtze River during the past. That's a lot. So in Tianjin, they brought 7 billion. So that's like Tianjin got 1/10, almost 1/10 of the water. Other Beijing area, other areas, they get more, of course. So this map shows the water use or water supplies. Water supplies is same as water use. Yeah, you can see before, this is before this project. So after this project, after 2015, the use increased because you have more water. So this one, okay, I'll use this one. Hope you can see this one. Oh yeah, you can see now, this project provides more than half of the total water use in Tianjin. I think that's great or terrible. That's more than half. Yeah. The big thing is that the deep water, the red one, the deeper pumping changed. Yeah. Now you can see almost stopped. In fact, they have documentation say that the government will totally stop the deep pumping in 2025. Yeah, will totally stop deep pumping. And this one, the Taiwan, that didn't change. That's a shallow pumping mostly for the agriculture. But that's a natural recharge and pumping can be balanced. So this is the water use compared before and after. It's 2014 and 2021. You can see a big change is this one, green one. Green one shows the use for the ecological and environmental use. They use a portion of the south water to recharge the natural, the lakes, the river at wetland. You know, the some of the water recharge to our aquifer. So now the aquifer works like this. First they stop deep pumping. And possibly they increase the recharge. Of course, we know that deeper aquifer recharge is very slow. It's very, very slow. But still, compared to the before, that's recharge faster than lateral recharge. So I think that's the reason why the immediate cause subsidence to uplift. So we process data with the INSAP, with Sentinel-1. You can see this is the data accumulated subsidence from 14 to 2021. You can see the Tianjin, 2/3. Yeah, only the central area low subsidence, 2/3. So the yellow one shows that 10 centimeters. So that means on average, most area have the minimal about several millimeters per year subsidence to 1 centimeter. So that's all. So I cut the time series. We cut the time series. You can see overall there is a trend around 2019. Yeah, 2019. So we did this kind of study. We use the data from 16 to 18 that represents the subsidence rate before. 19 to 2021, 3 years subsidence rate after, because the change. So 16 to 18 subsidence rate will same as, for example, before the 14. It's almost same. So we compare the subsidence rate before and after. So this is before. Like everywhere, you can see everywhere you have subsidence faster than 1 centimeter per year. After this after. Almost 2/3 of the Tianjin area subsidence stopped or below, you can say below 1 centimeter per year. So it's a big change, this map. This area, this is not Tianjin, it's Hebei province. Yeah. So I minus these two, yeah, subsidence rate before and after. You can see, so this is Tianjin area. Almost everywhere switched. Yeah, so the deep blue, that means the subsidence increased. The white area, that means no change. So this outside Tianjin, that means subsidence still increase. Yeah, this still increase 2 centimeters per year. But in the whole Tianjin area, almost the whole Tianjin area decreased. This was happened much rapidly than what I expected or what I thought. So my experience can be wrong, really. So there is one taxonomy test in this area. Yeah, so based on the publication my colleagues did, I figured out something a little bit new. So I figured out the new pre-consolidation height. So in this area, they found, so this is 1 year, 2018, they found that aquifer 4 contributed half total compaction of that year. Aquifer 3 contributed another almost 35 to 30. And then deep one, the 5 contributed about 10. They clearly found the aquifer 2 shows a slight rebound. So this is groundwater level in net 2. And this is one in the aquifer 3. So most of the subsidence, they don't have a groundwater measurement in aquifer 4, but clearly aquifer 4 contributed the most compaction. So I believe this data stopped at the end of 2018. Yeah, if we have new data, I believe that the groundwater level in aquifer 3 reached to this level, and the aquifer 4 also increased. So based on other observations, yeah, so I will show you a little bit later. So I figured out that this number, 14.5 meters, is like a new pre-consolidation height. So if the groundwater level in all the aquifers, deeper ones, reached about 45 meters, yeah, it seems like subsidence will stop. But we don't have continuous data. You can, yeah, but you still can figure out the rebound for some station occurred at 2019. So 2019's groundwater data more or less close to, in some areas, the subsidence stopped, close to new pre-consolidation height. We also found that, so they publish an annual groundwater map. I would say this map is not precise. You know, we play with the contour lines, we know that. But overall says that if groundwater level is above 45 to 50 meters, it seems the subsidence stopped. Of course, for new pre-consolidation height, we really expect it's a site dependent or at least town or village dependent. Historic one, we expect that it's really the regional. So I would say this is an important result for my researcher. Personally, I think, okay, that's our target. You need to elevate your groundwater level to about 45 meters. But in fact, I read with other publications that in Chinese, I talked with my colleagues, yeah, that's right. So historic pre-consolidation height in this area is about 20 meters. It started in the 1560s. So that means if they finish this compaction cycle, hydraulic height, consolidation hydraulic height reduced to 20 meters. So now it's 45 meters. Summary. Yeah, as subsidence community, we spend a lot of time to fight with groundwater. Yeah, we try to tell people don't use it, or we restrict them to use it. And also the government spent a lot of money to educate people to do the conservation, do a lot of things. That's happening exactly in Tianjin. Yeah, they don't, subsidence started in the central of the city. Yeah, they say stop. Then people, industry move to the suburban. Quickly, subsidence started in suburban. Yeah, just so I think they try to manage subsidence for two or 3 decades. I would say it's getting worse. Yeah, because the society needs water. Yeah, if you cannot use water, how can we generate so much things? Suddenly, because of surface water, immediately it's surprised. Immediately they solve the problem. I think it's not me who feel surprised, but many people working in the net subsidence in China, they will feel surprised. Yeah. So we really need to focus on the surface water. We cannot just focus on the groundwater. Okay, another very important is that your labels. You can see in Tianjin, subsidence is mostly in this side, the southeast side, northeast side. Anyway, it's all around the boundary area of Tianjin, of the Hebei province. Hebei province, they have large cities, industry, Tangshan, steel complex, Langfang, that's also industry. So they also got a portion of the south water. They also have the rules to regulate groundwater, but people need to use the water. So now subsidence mostly occurred in this area. So if you just follow your rules to regulate groundwater, you will not stop the subsidence in the bounded area. Yeah, you cannot do that. Yeah, because your neighbors, they still pumping the groundwater. So I think now the top level really need to think about that, okay, how can we totally do the coordination to use the groundwater as surface water? It's a redistribution of natural resource, in fact. This also happened in Houston, in fact. Different county, we have different rules to manage the groundwater use. As in the boundary area, it's always arguable. Yeah. Okay, I will report the results in both Houston and Tianjin in next meeting. I don't know what's the name of the next meeting. That should be the 5 years later. I hope I'll give you some surprise. Thank you.